And welcome to the third session of the 2025 ADIA Lab Seminar Series, Advancing AI for Image Analysis from Medicine to Earth. My name is Abdullah Al-Kitri. I am the chairman of the operations board at ADIA Lab, and I am a PhD student at Khalifa University. It's great to see many of you here today, and a warm welcome as well to those joining us virtually. This seminar is part of our ongoing collaboration with Abu Dhabi Machine Learning and ADGM Academy Research Center, exploring how AI can drive progress in climate science, health sciences, and within the digital economy. Today, we have an incredible lineup of speakers who will share some fascinating insights into emerging areas of collaboration, of exploration disciplines ranging from precision medicine to environmental monitoring. And following this evening presentation, we invite you to continue the conversation and join us for iftar. With that, let's get started. Our first speaker today is Dr. Farah Shamout, Assistant Professor of Computer Engineering at NYU Abu Dhabi, where she leads the Clinical AI Lab. Dr. Farah research focuses on developing machine learning methods for computational precision health. Drawing from this work, her presentation, Advancing AI for Computational Precision Medicine, will highlight how AI models can combine data from electronic health records, medical imaging, and other sources to improve patient care and reduce healthcare costs. Please join me in welcoming Dr. Farah.
Thank you. Thank you so much for the kind introduction and for ADIA Lab for hosting me today. So I'm very excited to talk to you about the work that we do at the Clinical AI Lab at NYU Abu Dhabi. And my research mostly focuses on developing AI models for real-world clinical problems. So we work with clinical partners in Abu Dhabi and in New York. And we work with real-world data, just to emphasize that. And it's also very nice to see very familiar faces from different walks of life, I must say. So this is great. So I'm going to start off maybe with this anecdote, which I saw at a conference and I really liked, which is the idea of hand washing. So I don't know how many of you know this story, but how many people here wash their hands? I hope everyone raises both hands up as well. But basically, when hand washing was proposed more than 100 years ago, it was actually a very controversial topic. So the first person who proposed hand washing noticed that the mortality rates were much higher in the maternity ward that was run by doctors versus the maternity ward that was run by midwives. And when he looked into the problem, he realized that many of the doctors would go to the morgue and then go to the maternity ward and implemented hand washing for a short period of time, noticed that the mortality rate dropped, got super excited that hand washing actually works, presented it at a medical society. He was Hungarian, presented at the medical society, but was completely shut down. And they completely ignored the importance of hand washing. He was sent to a psychiatric ward and eventually passed away from sepsis, actually. So I just want to bring up this story because it's, I mean, just crazy to think that hand washing took more than 100 years to be eventually accepted as a hygiene standard once germ theory was further investigated. And I like this metaphor because it reminds us that things in healthcare do take time. Like building an AI model on its own won't just change and impact healthcare completely. It takes actually a lot of partners, public health, regulation, the AI models, but also human factors research to make sure that whatever you build is actually usable. And when you compare that to ChatGPT, for example, it took 5 days for ChatGPT to reach 1 million users. So even with those technology nowadays, the more open access they are, the more, I think, user-friendly they are in the way they're presented, then the further reach that they're going to have. And this is just something to also keep in mind as we sort of dream about using healthcare, using AI to achieve impact in healthcare. So I'm going to talk about the work that we do in the lab, which is really led by my amazing team. So credits to them as well. But our mission is to help improve health outcomes by building smart systems that are built using real-world data in order to actually also work with the challenges that come from real-world data, like missingness, sparsity, etc. And we have two main interrelated tracks. The first one is to focus on the development of methodology and systems. So we train the models and evaluate them, and build specific sorts of frameworks based on the challenge that we're focusing on. But the second track is to also partner up with clinical entities and clinicians in order to identify meaningful problems, because we want to make sure that what we build on the long term beyond the research will be useful. So I'm going to frame this talk in the context of, let's say, three main objectives that we focus on when we approach any project. But I'll also give examples of how we tackle those objectives in the context of specific projects. So I did this the other way around, instead of focusing on the projects themselves. The first aim is to improve model performance. So a lot of the tools that we build focus on improving the downstream metrics, so improving accuracy, AUC, etc. The second theme has to do with enhancing robustness and efficiency. So currently we're looking at how can we best make the models more robust in the sense of also making them more compact, because a lot of these models now are really large in size and capacity. And the third one is to advance trustworthiness and reliability in order to make sure that the models are trustworthy from the clinician's perspective or from the end user's perspective. So we look at uncertainty, hybrid decision making, and so on. So starting off with the first one, which is improving AI model performance. So a lot of my work has focused on, actually, move here for the screen, on deterioration prediction to begin with. And with deterioration prediction, the main incentive is that a lot of the deterioration that goes unnoticed or unrealized in hospital settings could be due to staff burnout, understaffing, lack of expertise, and we saw that a lot during the pandemic. And when this tweet actually was posted, some clinicians got offended because it says patients don't suddenly deteriorate, healthcare professionals suddenly notice. But this has nothing to do with the clinicians themselves. I think it has to do with just the overload in healthcare in general, which is why many of these early warning models could be useful. And the second sort of main characteristic of the health data that we really prioritize is multimodality. I know the other speakers are going to focus on interpretability as well, but the main sort of priority for us in my research lab is multimodality. How do we take advantage of that? And what are the kind of challenges that you could face once you enter the realm of multimodal data? And in healthcare, this data can manifest in the form of wearables data, which we haven't really worked with much, because our main emphasis has been on medical images and electronic health records data. So EHR is the bedside data that gets collected from the patient, like vital signs, labs, their demographic information, procedures, and ICD codes. So for the first case study, this is the one from the work that we did during the pandemic. And the main sort of clinical use case for this was that when patients arrive to the emergency department in such a strained environment, eventually they might face three main adverse outcomes, which were admission to the ICU, intubation, or mortality. And when we spoke with the clinicians and radiologists who were working actually on the ground at the time, they prioritized this as the main use case at the NYU School of Medicine in New York. So when we looked at the emergency department and the kind of modalities that are collected there, most actually early warning models by the time were working on or were using vital signs data. So they were looking at how would heart rate, blood pressure, breathing rate, temperature change, 7 vital signs, and then compute an early warning score based on that. But during COVID-19, I think one of the sort of major transformations that happened then is that early warning models started also considering medical images like chest x-rays. And that's because chest x-rays as a modality became extremely popular. It was the first point of triage into the hospital. So we said, why don't we use chest x-rays to predict deterioration in this context? And we also considered other lab test results. So this is like a summary of the image classification model. So this is based on an existing architecture called the GMIC. And the GMIC model basically extracts information from the image as a whole, which is through the global module on the top, and then also focuses on the fine-grained details using the local module on the bottom, and combines both of them and has an interpretability element. But the key contribution here was that we first modified this model so that it works for chest x-rays, but second, we combined it with also a prediction using the clinical data. And at the time, And actually, even now, late fusion as a benchmark is quite a strong benchmark by just averaging the predictions, even if you calibrate before then. And we combined information that we learned from the clinical data, which was processed using a simple gradient boosting model, with the prediction using the chest X-ray image. And in terms of results, I think the main sort of insight that the clinicians were interested in here was that the chest X-rays do actually contain some useful information to predict deterioration. And the saliency maps that were produced by the model, even though it was a weakly supervised model, were actually meaningful. So you can actually correlate them with some clinical manifestation, which is beyond my expertise, but based on the few samples that we showed them, they did mention, for example, that some of the patches here were associated with like fluid in the lungs, which was also really interesting. And then we compared the model to 2 radiologists. So this is also something that we're interested in doing more as we go through our work, which is to always conduct a reader study. It's not always feasible because you need expert readers for a specific task. But what was interesting here is that even though the radiologists were not trained to predict deterioration, it's actually not within their scope of what they need to do in the ICU. They were able to predict it to a good extent, but the model did overcome them in some scenarios or performed comparably. Following that work, we actually decided to further dig into multimodal learning, and we stuck to chest X-rays and EHR, mostly because of the availability of public datasets. So the MIMIC dataset is a dataset that we commonly work with. And we've also introduced a benchmark called MedFuse that actually has the code that you need if you're interested in benchmarking models using chest X-rays and EHR. And following that work, we started looking into using self-supervised learning in order to learn general representations that are not task-specific and scaling up the number of tasks. So this work is currently under review called MedMod, but we basically introduced a new benchmark that has self-supervised learning methods if you're interested in that domain, like convert, align, etc. And we also introduced additional multimodal fusion approaches and evaluated it for additional tasks. So we currently evaluate it for decompensation, length of stay, and also radiology labels. Now, the main insights, I think, from this work is that actually self-supervised learning in this context does work, does lead to improvements in performance, considering the size of the unlabeled data during pre-training. But one of the things that we also realized is multimodal learning is not always effective in the same way for all tasks. So this is something that we're also currently investigating, which is when would additional modalities be useful from a clinical perspective for some given tasks. We also investigated the impact of multimodal learning in other use cases. So this work was in collaboration with a clinician at Cleveland Clinic Abu Dhabi, where we actually had OCT images of the eye, both the OCT modality and the infrared modality. And we wanted to predict what would be the risk of stroke, or what is the association between an OCT image of the eye and a stroke. And the results were very interesting because we were able to associate the OCT or the infrared with stroke with an AEC of around 0.6 to 0.7 with the 2 different modalities. And then the blue bars show the clinically informed model, which is the model that also incorporates EHR or clinical data. And we do see performance gains with the clinically informed model or the multimodal model, even with another baseline called RETFound, which was published by a different group, but they released the model as well. But it's a much larger model. I think it was transformer-based, whereas ours is based on a ResNet. For another study where we also focused on boosting AI performance was in collaboration with a fertility clinic called ART Fertility Clinics. So with them, we actually processed a very large data set consisting of time-lapse imaging of embryos. And we did multiple tasks. The first task was to automate the labeling of which stage is the embryo at. So is it at a 2-cell stage, 3-cell stage, or has it reached a blastocyst, for example? And the main objective there was that it's a very time-consuming process for embryologists to just sit down and label the embryos and check at which stage they're at. And it's also a very expensive process for patients because it's time-consuming, but also financial burden. And then the second task that we did was predict based on the time-lapse imaging, and based on the earlier stage as well, at whether the embryo is going to reach to a mature stage ready for transfer. which means that the embryo can be cryopreserved or actually be transferred for the IVF further stages, so pregnancy, live birth, etc. And this was a very interesting project because we started looking at not just using a single image, but also using a sequence of images in order to predict the associated outcomes. Performance of the model is very impressive. So most of the results that we had were above 0.96. And we also had very strong baselines, which are considered state of the art. So this work is also under review. It'll be out soon. So that was the first objective, just to give you a sense of what we do from a model performance perspective, but also what other research groups do, because this is currently the state of the art, which is to combine multiple modalities that could be useful for a specific task in order to boost performance. But boosting performance is not always the only objective. So the second objective that we are currently prioritizing is enhancing robustness and efficiency. And by robustness and efficiency, first I'm referring to making the models more compact, but also with a good performance, because as you already all know, many of the models that are currently coming up now are exploding in terms of size, both in terms of the number of parameters, but also the amount of data that is required to train those models. So I think a very important question that we should consider as AI researchers is, how can we also leverage existing models? Like, why do we always need to train models from scratch? Why not use an existing model in order to train maybe a smaller, robust model that can still achieve the objectives that you seek? So, to this end, we're currently working on, this is one paper where we designed a knowledge distillation framework by using a larger teacher, and in this specific setting, an ensemble of teachers, that can then help fine-tune a smaller student network that is smaller in size, but still achieves the same performance. And we're also focusing on the multimodal setting because we want to make sure that we're using the relevant modalities for a specific task. Some of our earlier work also looked into zero-shot learning. So in the context of robustness here, what if you use a model in a new setting for labels or diseases that weren't seen during training? And in this study, we also found that by learning from the semantics of the image and the associated labels, you can actually then do well in a zero-shot setting, as long as the semantics have been learned even from the seen labels. One other area of interest for different work is federated learning. So just for context, for those who are not familiar with federated learning, but the idea is that you have some data that is scattered across multiple clients, and you want to learn sort of a joint model without having to share the data. And most of the frameworks that we found either focused on the horizontal setting or the vertical setting. So horizontal federated learning basically entails having the same modality at different clients for, let's say, different patients, whereas vertical federated learning, you have data for the same set of patients dispersed across multiple clients. But realistically speaking, in a real-world medical setting, you could have a combination of the two. So the patient's data could be dispersed across multiple clients, but you could also have the modality for the same modality collected for different patients at different hospitals. So in this preliminary work, which is also under review, we actually designed a new federated learning framework that combines the two. It could fit under, I would say, the area of hybrid federated learning as well, but the unique element here is that we actually combine them within the same framework. So eventually the model that is used, which is GM blended, actually learns from the unimodal encoders and the multimodal encoders across the different clients. And this is also an area of interest for us. Now, the third objective, which I believe is also extremely relevant in the context of medicine, has to do with how do we make these models more trustworthy and reliable from the user perspective? Because as I mentioned, we also want to make sure that what we build is trustworthy for clinicians and useful for clinicians. And all of this is obviously in the research setting. We're starting to look into translation, but I'll start with the first relevant paper, which has to do with breast cancer detection. So for this work, we were interested in enhancing breast cancer detection, so also focused on performance. But one of the things that we wanted to look into is how do you combine the predictions of the AI model with the predictions of human radiologists? So here we also worked with a large data set collected at the NYU School of Medicine. I think one of sort of the main steps of an AI medicine pipeline is to pre-process the data. and we actually spend a lot of effort, a very substantial effort on data pre-processing for most of our projects. So this is the general architecture of the model, where you have a sequence of images collected from within an ultrasound exam, and then you process one image at a time, and then combine them all through an information aggregator. In terms of reliability, I think one other important element that is currently considered a standard, I would say, in AI for healthcare is to always test on an external test set. But I wouldn't say it's always guaranteed, because you do need a good external test set that has good labels, or that was labeled in the same way, that is of good quality and size. So in this work, we compared it to publicly available data set that was published by, I think, a group in Egypt. And the model performed well in the external test set, but the performance did drop slightly. And we also compared it across different patient subgroups based on age, breast density, or the manufacturer of the device. But I think these kind of results, which are currently, I would say, considered expected in the area of AI for healthcare, is really useful in order to investigate how would the model perform for different patient subgroups or different subgroups of your target population. But this is the most, I think, exciting result, which is combining the predictions of the AI model with the predictions of the readers. So here we had 10 expert radiologists at the NYU School of Medicine, R1 to R10, and the blue bars show their performance on their own. So we constructed a test set that they would need to mark and say, is there cancer or no cancer? The purple bars are the bars that basically just average the predictions of the reader with the prediction of the AI model. And the red dashed line is just the AI model on its own. And I think what's interesting here is that through hybrid predictions, you can actually get better performance relative to both the AI model and the readers across maybe most of them, but not all of them. And I'm not showing it here, but when we compared it as well with respect to, let's say, biopsy rate and other metrics, I think the hybrid model is very interesting and worthy of further investigation. And there's more details in the paper as well. So another area of work that is led by another PhD student is quantifying the confidence of the AI models. So currently we are looking into mostly enhancing uncertainty quantification for model selection purposes. So in order to select better models that are more confident about their predictions. But the idea here from a clinical perspective is that the AI model would compute its prediction, let's say for breast cancer, but also indicate how certain or uncertain it is about its prediction. And if the risk tolerance, let's say, is low, or the risk tolerance is high, you can then defer some cases from the AI model to the human for additional review, or even maybe to a second reader, third reader, fourth reader, depending on the application, because for some applications, you actually do need multiple readers. And this is currently an ongoing and active area of work that we're looking into, which actually overlaps a lot with regulation, usability, interpretability, and so on, because the uncertainty quantification could be useful in many different dimensions, both from a model selection perspective, but also maybe from an interaction perspective between the model and the user. Another work that I think I'm very excited about, and so is my team, is MedArabic. So in this study, we first ventured into evaluating LLMs on the goal was to evaluate LLMs for Arabic-speaking populations in the context of telehealth. And I'm very proud of this work because it was also proposed by an undergraduate student, and then we built a great undergraduate student team who are currently working on it. And one of the main challenges that we faced was that there are actually there aren't any good data sets that use or that focus on medical tasks and use the Arabic language. And so one of the things that we try to do is, let's say, maybe translate existing data sets. But the main worry that we had there was data contamination. So we were pretty sure that, especially with the GPT and all of these models, they are using a lot of publicly available data set. So they are likely going to use, let's say, for example, one data set is Al-Tibbi, because that's posted online. And actually, when we tested out some translation and then tested the model, many of these models actually use translation as a feature. So they might translate from Arabic to English, answer the question, and then translate back to Arabic. So it's more of a translation problem, let's say. So what we did here is we constructed a new data set, which is called Med-Arabic. Currently, we have 700 samples. We used a set of past exams that actually are not posted online in a structured way and are not readily available. And we had multiple choice questions, and then we had multiple choice questions with some injected bias, fill in the blank, patient-doctor Q&A, which was using an existing one. This is publicly available. And then one of the things we also incorporated was some NLP techniques to modify actually the ones that are publicly available, which is dataset 5, in order to check if the model is memorizing anything. There are other techniques that we're currently looking into. But what was interesting here is that actually the models need a lot of work in the context of Arabic. And the best performing models, which were in this case GPT-4, Claude, and Gemini, on these tasks, also struggle with bias. We also tried some bias mitigation strategies, but there's still more to do. So I would say this is also a very exciting area of research. We're scaling up the data, so hopefully very soon we'll release the larger data set. And I think that so far we've reached more than 1 million tokens, so it's going to be actually quite large. And I think the very cool thing about this work is that it's very interdisciplinary. So we're working with an NLP specialist, NLP tools to process specifically Arabic data. In terms of ongoing work, so we're currently working towards building multimodal foundation models, so building on the work that we already have. We're engaging very closely with clinical partners. And one of the sort of new ideas that we're currently looking into, which is also, I would say, a priority for Abu Dhabi, is healthy living and longevity. So we're also investigating ideas in that domain, because I think what's really interesting there is, why should we wait until individuals get sick? Why not actually build AI models for maybe performance athletes, but also the average, I would say, individual like me, who might get sick, and I get sick every once in a while. So I think these are the kind of questions that we're currently tackling with from a medical perspective. But from a technical perspective, we're integrating additional modalities and focusing on the objectives that I shared, obviously, which are tailored for the clinical problem that we work with. We did host a clinician bootcamp last semester, but we're interested in hosting more, because I think one of the things that we realized that the projects get much better in quality when you engage the domain experts, which is really important. And overall, in terms of the guiding principles, which we prioritize in the group, which are to identify clinically relevant problems, understand the inherent characteristics of the data, because it's real-world data, so it's noisy, design and develop end-to-end models, and also advance reliability and reproducibility, both in terms of open sourcing code when possible, but also from a trustworthy perspective. And I think I want to stop here just to also thank the team. And is time good? Yeah, thank the team who do a lot of the amazing work. Kongbo, the postdoc, Shaza is an RA, and Julian, Dima, Bara, and Said are PhD students. And also thank our partners who we work very closely with, and some of our funders like the Center for AI and Robotics, Cities, and others. So I'll stop here. I think we have some time for questions, and you can also always reach out if you have other questions.
We have time for a few questions. Please raise your hand if you want to ask.
Thank you for the great session and the information and what you are doing. Now, what's your source of data?
So it depends on the project. For example, for the chest X-ray stuff, we're working with Mimic, publicly available dataset. It has around 200,000 images and EHR data. But we're currently looking into getting more data from the School of Medicine and a local clinical partner. For the fertility project, it's also the local clinic called ART. And the OCT is with Cleveland Clinic. So every project has a different partner. Yeah.
Thank you.
Thank you.
Yeah, also my question follows up is about the data. Typically, all this model needs a large amount of data to work, multimodality, deep neural networks, and so on. And there are public data sets, but they are usually regional, like US data China data. And of course, this regionality does not imply that you can use them wherever. Use them in Europe, and then because climate condition, tradition, and whatever is different, and so the incidence of different problems is different, it has to be adapted. So how do you deal with this localization and let's say specificity in your data set? Or maybe this is just UAE data, I don't know.
Mimic is US based, but we've only worked with, like, in that project, a US based data set. We're currently looking into incorporating a UAE one. But I think there's a lot of work in that area. I think there are many researchers who focus specifically on out of distribution and like distribution shifts. We haven't worked on it yet because we're currently focusing on like a single setting data set, I would say. But I've also seen actually some papers recently that have combined data, let's say in the context of chest x-rays, because there are many chest x-ray data sets. So there are a few studies like EVA-X and a few more that actually combined the chest x-rays and trained with all of it at once, and then showed that the performance is still fine. So I think maybe once you get to the domain of very large data, the differences might become less significant, but should still be like assessed for during evaluation. So I think as long as that we're assessing for them during evaluation in a conscious way, we're not just completely ignoring the fact that they come from different sources. I think that's a good exercise.
Okay, thanks you.
Yes.
Thank you for your presentation, Dr. Farah. I think you're working at the cornerstone of two very key industries, that is AI and healthcare. I had a specific question about the radiology model, the hybrid model that you proposed. In the results of that test that you had done there were only 1 or 2 doctors who had outperformed AI with the hybrid approach. So based on your experimentation, would you say that...
This one?
Yeah. Would you say that the future of AI lies in a hybrid approach or lies in the AI replacing the doctor completely?
I would say it's the hybrid approach. And I mean it. Sometimes people say it, but they don't mean it. But I really mean it, that it's the hybrid approach. I think it also depends on the setting. So let's say you work in a low-income setting with lack of resources where you actually have shortages of radiologists. I would say, yes, let's consider an AI-only model. But I think in a setting where you do have good human resources and can afford to actually get your, let's say, human resources to even evaluate or collaborate with AI models, then I think that's the best way forward, depending obviously on their expertise. Because even in the study, the readers that did comparable with the AI model were actually the ones with the highest years of experience. So again, depends on the setting, depends on their expertise and years of experience, and depends on the resources. Yeah.
Thank you.
Thank you for your talk. Very much enjoyed it. And I want to ask a question following up to the previous question. And so in 2016, I believe Nobel Prize winner Geoffrey Hinton famously made this prediction that we should stop training radiologists in 5 years. AI will completely replace radiologists. So I wanted to ask you, since you're working in the field, why this didn't happen? And you gave some reasons, but I think it would be good, maybe also as a iftar dinner discussion, why these predictions are being made, and then it's much more challenging in reality to make good on the promise of AI.
Thank you. That's a really good question. And I guess it's been 9 years, not 5, since his prediction. I think in 2016, I was also starting my PhD. So back then, people were starting to look into like LSTM, and transformer models became popular also throughout that period. And I think why did that not happen? First is access to data, because I think access to data really got better post COVID-19. It's still not great, I would say. It has improved significantly, but we still don't have, I would say, like maybe also depending on the context and the jurisdiction, but like effective ways of sharing large-scale data sets. Maybe the UK Biobank is a very successful model, but again, they're very specific to a specific task as well. I think the other thing is also testing. Maybe many of those models that are currently being developed or have been developed or haven't been through sort of the full pipeline up to translation and testing in real-world settings. which I think is also hindering why AI is not replacing radiologists in that context. And I think the other thing is lack of awareness and maybe education. I think from my perspective, from engaging with clinicians, but also with non-clinicians, I think AI now must be incorporated within the medical education. And I know some schools are already doing that. So I think eventually it might not replace them, but change the type of tasks that they do. But I think we will always have radiologists, at least in the near future. Yep.
We have time for one more question.
Yes. Okay, excellent. Going back to the first question regarding the data quality, the source of all this data has to be based on evidence or the best available information. We have a bit of an epidemic with paper mills, even the source of the science. So the model will obviously collect whatever is out there. So you mentioned something that we should use existing models. What's your view on using legacy clinical decision support systems like UpToDate, which is the gold standard, that have gone through the process of filtering, grading information? Because at the source, okay, images is the low-hanging fruit, but when we go to clinical decision support system at the point of care, which is the golden objective, yeah, that's the problem we're going to encounter.
Do you have a specific example of like a CDS tool?
Yeah, UpToDate. UpToDate is part of Wolters Kluwer. It's used by 1.8 million doctors. They got 7,000 or 8,000 doctors that have gone through the whole editorial process. Of course, it's very text-based, but it's the best available tool out there. I don't know if any doctors here know about these systems. And they're very fastidious because they go through all the studies, because every day there are thousands of things. Triage is not perfect, but it's probably one of the most trustworthy systems. So why don't piggyback on that? Why don't piggyback on Philips and other existing systems that come from PACS and see how you could do something really great together instead of starting from scratch?
Yeah, agreed. I think there's some work, maybe not, I don't know if they're using the one that you mentioned specifically, but now because of LLMs, there's a lot of work actually that looks into bringing in external knowledge from other resources, like in the context of fact checking, for example. So you can very much check for additional sources of information just because the models also got better. And I've seen that, for example, in the context of referring to clinical guidelines, like I don't know, not the tool that you mentioned, but let's say books that have information related to clinical guidelines. There are some papers that utilize that information. So I think you will see more of that now because everyone is looking into multimodal LLMs, vision language models. Like this is the time where we're actually starting to combine different modalities using much larger data sets. So I think it's up and coming. And there is some existing work in that area. I'm just not familiar with all of it. Now, why do we not do it with vendors? I would say maybe there are other like practical reasons that need to be considered as well in terms of establishing. I think this is also a good point. Like we do need more industry, academia partnerships in the UAE as well.
But I think it's because guidelines is only one of 20 different sources of data. And see, it's worth to explore with the vendors. It's not, I mentioned there's lots of vendors. Clinical decision support systems have been around for 30, 40 years. So I think I would encourage you to look into that because they are really good at selecting what's right or maybe not so right.
Look forward to talking more about it. Yeah.
All right. Thank you so much, Dr.
Thank you.
Farah, for sharing your work with us. Thank you for the great presentation, Dr. Farah.
Thank you so much.
Our next speaker is Dr. Dwarikanath, Principal AI Machine Learning Engineer at LocAI. Dr. Dwarikanath's expertise lies in examining foundation models in medical imaging and improving generalization for diverse medical applications. In his presentation, Interpreting Foundation Models for Medical Image Analysis, he will discuss the transformative potential and challenges of those models in medical image computing. Dr. Dwarikanath, the floor is yours.
Hello, good evening, everyone. First of all, I would like to thank ADIA Lab for inviting me for the seminar. And so the topic of my today's presentation would be about interpreting foundation models for medical image analysis. So before we go on to that, I'd like to give you a brief background about myself. So I did my PhD from the National University of Singapore way back in 2011, where my thesis was focusing on medical image analysis, developing computational models for time series medical image analysis like MRI. Then I worked at ETH Zurich, Switzerland as a postdoc and had stints at IBM Research and Inception AI in Abu Dhabi. IBM Research in Australia and Inception AI in Abu Dhabi. So, and right now I'm working at LocAI. And my research interests are primarily in the field of machine learning applied to healthcare with a slight bias towards medical images. But I also work a lot on computer vision and multimodal data, combining image and text. And one of the very interesting areas and something that I've been working on for a fair bit of time is about interpretability. So now with so many models, machine learning models, foundation models, large language models coming in almost every week, we see a new release. So so there is the interpretability aspect is a very important thing here. Particularly nowadays with trustworthiness, there are so many concerns around trustworthiness in AI. How can we, be really confident that the outcomes or the results being given by the model is actually reliable? So how can we, and then there is also privacy preserving. So the umbrella of privacy preserving or trustworthy AI is pretty broad. And within that, I would say interpretability is one small maybe, but quite an important aspect. So interpretability, so how does it, so I will be presenting most of the stuff in the context of images, medical images in particular, but these principles and these techniques are applicable in a lot of other domains, not just in computer vision dealing with images, but also in a lot of other domains. So to start off, deep learning, we probably are, many of us might be aware, the revolution took off around 2012, 2013 with AlexNet and with the ImageNet data set. So initially there a lot of work on computer like image analysis. And then gradually with time, they also caught up with the deep learning revolution. And we see that this is basically a chart showing how the number of papers in different conferences increased in the medical imaging topics. So there were, it's all grouped under modality, which is, modality is in this part, the MRI, then the segmentation or the task specific, this is the anatomy specific. And with development of new models that were beating state of the art, now the question came, how reliable are they? Previous models, like what we call now the classical ML models, like let's say random forest for classification or support vector machines, they had a certain element of explainability, in the sense you could actually understand how the model came to the final decision, but not so in deep learning or the CNN models. So it was like a black box, and the whole, then there was a lot of effort into opening this black box and try to understand how to make sense of the output. So this is a chart showing, the level of or the degree of explainability versus the prediction accuracy of certain models. So anyway, so here you can see the best prediction accuracy is deep learning models, neural nets, but they score very low on explainability. But whereas something like decision trees, very good on explainability, but the lowest in terms of prediction performance and all. So as we can see that as the prediction accuracy improves, the explainability or the interpretable part actually becomes less prominent. So then actually at one point of time around 2017, 2016, there were questions being raised. In fact, there were debates about how to define interpretability. What is interpretable AI? Then so this is like a very like a a simplistic explanation or a definition that interpretable ML algorithm is one which there is the link between the features and the output can be made used by the model, and the prediction can be understood by a human. So this is particularly critical in very important or critical fields like healthcare, where the outcome can decide not just can be the question like factor between life and death, but it may not go to that extreme. But there are other aspects like insurance, then diagnosis. If the diagnosis goes wrong, who is responsible? If it is predicted by a model, who is responsible? So all these questions were being asked, and then people started developing frameworks to define this explainable AI and all that. So I would just, since we focus, like I focus particularly a lot on images, and CNNs have been a very popular tool. I mean, we could still say the same thing about transformers. So basically, the idea is that if you have this neural network model, and you have these different layers, how do you understand? How do you make sense of the output of different layers? So we all know these like earlier layers are low-level features, the mid layers are mid-level features, and high-level features related to shape. So low-level features pertain to edges and or texture. Then high-level features are more like overall context, shape, and all that. And mid-level features are a combination of the two. Or you could also people started working with, like for example, these early works. They looked at after training neural network models, how can you look at the prototypes of different classes? Because let's say in this case, class of goose. So because there are images from a wide different cameras, different backgrounds and all, so you'd see there are different shapes of the bird superimposed. But the idea is that it's conveying here is that these filters or these different layers, they learn the shapes, the essential characteristics of their particular class, which may be a goose, which may be a car or a plane or anything else. And then once this was little advanced, this kind of study. So then people started looking at specific parts of the image. So if you mask certain parts, how would it affect the outcome, the classification performance? So that kind of was like to give some level of importance to each part, which was whether, like, for example, here, if initially the probability of this being a tree frog is 0.54, and I mask out these background, the probability increases because it highlights still the most important parts like the mouth, the eye. But the interesting thing is probability increases. Why? Because it masks out a lot of background, which is non-essential, non-informative information. And then if you mask out the main defining characteristics, you get very low probability. But if you just mask out a bit of the background here and there, it doesn't change the probability by much. So these kind of gave a deeper insight into what works, and then like what exactly is the informative part of an image. And that same concept was also started. It was also explained with other data, like particularly language, NLP and all, where people started like when you pass set of words, which words are more important, the context length, and all these became very important research outcomes. And then there came GradCam, which was more like this shows like a heat map, which tries to understand which, like for example, if the model is predicting that this is a cat, where is it actually looking? I mean, looking in the sense that which part of the image gives the best or the maximum information for the model to make this prediction. So yeah, here it looks at I mean parts of the cat. Then the original model, then it was improved upon using ResNet, and then it slightly improves. So this then kind of people started developing techniques like, for example, this was one of the first techniques, guided back prop, and then there was guided GAD-CAM, guided GAD-CAM. And they were not so, I mean, we can see it's not very informative in the sense that we just see like an edge image, but how to make sense of that and all. So gradually people started working on these interpretable models. We call this CAM basically stands for class activation maps, and so it was found that this heat map kind of representation was the best, I mean, most intuitive representation. You could relate to where the particular important regions and all. And then there were different studies that came out for sanity checks for saliency maps. How do you determine which is the best? I mean, so this is actually a list. I mean, this is not an exhaustive list of the methods, but you can see there are so many different methods. How do you understand which one is the best and all? And one interesting study that was conducted around, the results came out in 2022, was the recognition of patient race medical images. So there was this data set where the information was available about the race of the different patients, and so some researchers, they kind of trained a model to predict. First of all, it was for all, like entire data set as it is. Then they started identifying which are the most important parts of the image. Like you see this whole highlighted thing, heat map thing. So this was for lung or lung disease prediction, and they found, okay, intuitively we can say this area is the most informative. And then they masked out this particular part of the image, and then again they did the same set of experiments. And what did they find is, so like this DenseNet 121 is a model, the CNN model, then with the mask. So for the Asian ethnicities, and the black ethnicities, the performance dropped significantly. But for the white ethnicity patients, so the performance drop was, there was a drop, but not as significant as the other two ethnicities. So what this basically tells us is that there's a lot of bias in the data, that it is biased towards a certain group kind of people for whatever reason, because it's the way data set was collected. But the most important takeaway message is that because of the interpretable components, so researchers were able to identify which is the most important part of the anatomy, which helps to make a decision, and and I mean, exploring that further led to these insights, like there is bias, or you can even recognize the race of the patient. So I think that if we read this paper in detail, it gives us more insight into what can be interpreted from the data using these interpretable models. So although, I mean, some of the like the previous result or the paper was a bit can be deemed to be controversial, but the main point is this interpretability models, or the interpretability outcomes, they can be understood as like fingerprints, like unique to a modality, unique to a patient, and unique to the particular application that we are looking at. So if we have like this is a general representation, X-ray goes through a model, gives us a saliency map, and so researchers have used it like in different applications, where instead of using the entire image, they take the saliency map and do analysis. And for example, one application is image retrieval. So the advantage is that there are actually two advantages. One obvious advantage is the amount of pixels we are dealing with processing is much less than if we were to use the original image. The second advantage is it gives a much more focused information. If you look at the whole image, there are a lot, I mean, the original image, there are a lot of irrelevant things which really don't contribute to the overall final decision. But looking at the very focused informative regions helps us to improve our performance, the model performance. And you can also do it in not just that, but also in very critical applications where like neuro-oncology, where there is radiation decisions to be made on radiation doses and radiation location. So there you can see that if you have this kind of saliency maps, it helps you understand better which is like a disease region and where we could focus our targeted radiations and all. So then there's something also that which I have also worked on is in active learning and zero-shot learning for classification. So I'll talk a bit about active learning in the next slides. So basically, what exactly is active learning? Active learning is a method where you make with the minimum number of annotated samples, you make best use of you extract the best performance of the model. So why it is relevant? So if we step back a bit, a few years when whole deep learning revolution started, one of the major factors, of course, being the release of huge public data sets. These data sets had a lot of images, but the quality of the images were not good in terms of there were some noisy labels and all. So by using active learning, we are actually selecting the best quality samples and feed that to the training data. And even now, also it's a well-established fact that data quality is more important than data quantity. So as we can see, if we add more and more quality data, we are getting better representations. And then there is also like, for example, this particular pipeline was about taking images using trained classifiers, getting saliency maps, and then doing ranking or finding informativeness of different samples. Then I'll talk a bit about foundation models. So foundation models, they are trained using huge data sets. But once they are ready, it's very difficult to change their weights. And particularly, a common scenario is if we are accessing it through an API and we don't have access to the weights and all. So how can we extract such kind of information like ranking or interpreting their outcomes? So there is something called zero order optimization or ZOO methods, which give one input and then a slightly perturbed or a changed input, and they look at the difference in outcomes of the foundation models, and then they try to infer ways to train another kind of it can be a classifier, it can be a segmentation map or something. So this is something that we worked on. It's a fairly recent work where we train visual prompt decoders that can help us identify which are like given an image to a foundation model, what are the explainable components or more things that can in terms of visual representation. And once we actually have that, we can use it for different things, like it can be for ranking sample informativeness, or it can also be for understanding more about the training process. And so the last few slides. So how do experts or other clinical experts, doctors in this case, perceive interpretable AI? So many of them, like this was from a poll of 80 responders, and they had different levels of experience and they're working on different fields. So first thing is, the question was asked, do you need interpretable AI? Significant percentage said yes, they want to have security about their answers. So that was in the early stages when still clinicians were not open to the idea of AI systems coming in. They thought that will replace them, but so they were a little apprehensive. But quite a number did say that, yeah, they want this interpretable AI. And what kind of information would you prefer? It's like something that it's visual cues. Some said some kind of description statement. Some said it doesn't matter as long as it is understandable and not time consuming. So I think these two like descriptions and visual highlights were the two most relatable outputs. And then which aspects of interpretable AI is most relevant or critical? So safety and efficacy. Basically, it should not put them in a spot, because life and death decisions are done based on that, and they should be able to. It should be effective and efficient. Should not be a very time-consuming process. Right. So just then to wrap up, so interpretability systems, they don't have to give you every level of information, but just enough so that it can help you make the decision. And like this, it's not to understand every part, and we should be able to make a correlation between the intermediate output process outputs and the final outcome or the decision. And so these, I mean, particularly in healthcare, these should be integrated into systems so that doctors can explain why they are making certain decisions. And yeah, of course, it's still an underexplored area, I would say. So still a lot of work coming out on this area. So yes, so this is my final. Thank you very much.
Thank you so much, Doctor. Due to the limited time that we have, we only have time for one question. And then we will be available during iftar for further questions and discussion. So we have time for only one question.
Thank you very much for this beautiful talk. Very interesting. In the beginning of your talk, you had a slide about explainability, and you mentioned in the very beginning, first or second slides. How do you quantify? I mean, what kind of measurable quantities do you use in order to quantify explainability? And this is
right. So explainability, I mean, in my opinion is that it's difficult to quantify the explainability, but what we can do is it's more like a assessment. Like if we assess a certain explainable approach and how does it help in a particular downstream task. For example, if doctors are able to get better, more efficient, it saves time, or it improves their performance, it improves the decision-making performance. So based on those outcomes, we can say a particular method is good or bad, but it's difficult to, I would say, quantify that or even the level of explainability. I mean, at least I think maybe there are studies which correlate, maybe rank certain methods, but giving a absolute score is a bit of a challenge.
Yeah, I think that should be a very interesting topic for discussion and for research.
Absolutely, yes.
Thank you very much for your talk.
My pleasure.
Thank you so much, Doctor, for your great presentation. Dr. Dwarikanath will be available during iftar for your questions and further discussions. For our final speaker, joining us is Muhammad Sohail, a PhD candidate at MBZUAI, specializing in large vision language models for Earth observation. Building on his work on GeoChat and GeoBench VLMs, Muhammad will introduce us to the potential of conversational AI for interpreting geospatial imagery in his presentation, VLMs revolutionizing the analysis of Earth observation data. Please join me in welcoming Muhammad.
Hello, everyone. My name is Mohammad Sohail Danish. I'm a PhD candidate at Mohammed bin Zayed University of Artificial Intelligence. Today, I will be talking about GeoChat, which is a grounded vision and large language model for remote sensing and Earth observation. So, if you look at the recent advancement in the remote sensing imagery analysis AI model, they are really task specific. For example, we can find a model which can only use for the land cover classification. For example, if we give an image, it will tell us it will classify if it is a forest, water, or an urban area, and so on. Another we can find model for the change detection task. So here the goal of the model is to basically assess the, for example, effect of the deforestation, or the tell us how much damage has been done due to the disasters like fire and the flood and so on. Then we will have the sensor-specific models. So, for example, there will be models specifically trained for optical remote sensing imagery, or the SAR-based imagery, or the hyperspectral imagery. And then most of the models we will find will work only for the images, and the user cannot basically query them using natural language and so on. And even if we find some models that do input the textual input, do take the textual input, but again they are very task specific. So they kind of lack ability of this conversation which we need. So if you look at the recent advancement in the generative AI architecture, like they are really transferring the way we used to communicate with these AI models and these AI agents. And their main capability, for example, of these large language models like GPT and Gemini, their focus is like conversation capability. Like for example, user can input a natural language query, and model can understand that query and generate a human-like answer according to that query. But one of the downside of these like great works is like they are the closed source, and we cannot use this model and build on top of these model, like our application on top of these closed source model. Another is like they have the very generic knowledge, which is not very specific to, for example, remote sensing domain. And also there is some sort of lack of transparency in terms of like their data set. They do not share like which data set they use for the training, and what was the exactly set of rules they use to basically generate that response according to based on the user query. And also there is like a lack of multimodal capability. So even though right now like GPT they can accept the images, but they only accept the RGB images. But in the remote sensing, we have like multispectral imagery and hyperspectral imagery, and still these models do not take this kind of input. So the idea is to basically have a unified model that can basically combine these all individual tasks into a unified manner. So we proposed GeoChat, which basically combine these suite of the tasks, starting from the scene classification, where the goal is to basically classify a given image into, for example, a rural or an urban area. Then the task of the image capturing, where the goal is to basically describe an image, give a detailed description about the image, what has been input to the model. And also the region capturing. So in the remote sensing imagery, usually the single image can cover a wide range of the land. So but if the user is particularly interested in the really small area within the image, so that's a task of the region capturing. For example, in this image, user is interested in this blue box, what's in that blue box, and the model tell like there is a small card which you can see. Another task we discovered is the visual question answering. This is like generic open-ended question answering task, where user can ask any open-ended question based on the image, and model will try to answer that. Then there is a multi-turn conversation. So in the multi-turn conversation, basically a user asks one question, and then it shifts to another type of the question and another type of the task, and the model will basically continue to follow up, like user will follow up a question, and model will try to answer that. Next is the referring expression. Basically, so here the goal is to basically when the user give a description of the object, the goal is to basically localize the object within an image. For example, when the user gives a prompt, basically tennis court at the bottom, so the goal here is to basically give those bounding box coordinates, for example, this red box, based on the query of the object. Another is the phase grounding. So in the phase grounding, like this is the image capturing, but with the bounding box information as well. So idea here is when models give us the description about the image, it should really pinpoint the objects which it is referring to in its caption. For example, in this image, when the model talks about the multiple buildings and the houses, it should also pinpoint like these blue, like you can see the houses in the red and the yellow boxes. So it's referring to those boxes. And for example, when it talks about the trees, it should localize those trees which it's referring to. And similar, the tennis courts and the number of the tennis courts and so on. So the general goal is to basically make this earth observation capability open for like generic user and non-expert users. So these are some key highlights. So we proposed like a large visual and language model that can perform this suite of the tasks ranging from image capturing and the region capturing, visual question answering, to more complex tasks like the grounding and the referring expression. To train this GeoChat, we do not have like already publicly available data set. So we designed a specific data set generation pipeline that utilize already available data sets in the remote sensing domain, and then we can generate these image text conversation pairs. And we also propose a benchmark as well. I will quickly talk about the architecture of the GeoChat. So I will start from the bottom. So given the remote sensing image, the model basically first tokenize it, and then we pass it to a vision encoder to get the vision features, visual features. So in our case, we use the CLIP VIT model. So once we have these vision features, now we use a MLP adapter network to basically project or the map these vision features into a space which LLM can understand. So after these projected features, we basically enclose them into this specialized token called IM_start and IM_end, and then we append task specific identifier or task specific prompt. So what are these specific prompts? So these tells model like which type of task user is interested in. For example, in the case of the referring expression, where the user is interested in localizing the object based on its textual description. For example, the question was like user is interested in the football ground, which is on the right side of the image, surrounded by the trees. So based on this query, and now user wants the bounding bosses, we will start with the token of the refer. This token will tell the model, okay, user need a bounding box, so it will predict output a bounding box. Similarly, for the region capturing, we use the identify token. So it will tell model like user will give you a box, and it want to answer specifically to that box within a specific part of the image. And we have the other like image description in the VQA model. So I'll quickly now talk about the data sets. So we use these already available data sets like object detection data set, visual constant and answer data set, and the scene classification. Notice these none of these data set provide these image and text pair conversation model data set. So we come up with our own data set generation pipeline. Sorry. So we will start with basically extracting the attributes of the object. So given an image, first step is to basically identify, locate those objects, and then extract those objects attributes. Attributes could be like their category, if it's a plane or the shape, their color, their relative size. So for example, is ship in the image is relatively smaller than other ships, or it's larger than the other ships, and their relative position. So we can extract like if this ship is located at the top of the image, at the center of the image, and so on. And then we will extract their spatial relationships. So for example, if car is parked in the parking lot, or it's driving through a road or a bridge. So here is an example of the annotation, our annotation pipeline. So given this image, we will first have these objects attributes. For example, blue ship, blue box ship. So we can extract its white color. It's relatively small in size, and it's located at the top left of the image. Once we have these attribute information, next we will use these template matching from where we basically generate small sentences based on those attributes. For example, we can say like there is a small gray ship which is anchored at the harbor at the bottom right, and we can similarly say some trees are located at the top right of the image. So we will have these short sentences for this whole image, and now we will use those short sentences to basically prompt an LLM to basically mimic this conversation, where LLM will generate a question and also answer the question based on the information we have provided. So overall, this will give us like conversation annotations and the detailed description and so on. So these and then we will use these annotations to train our GeoChat model. Here I will show the quickly demo of the GeoChat, like it's a UI which we use. So here the user will upload an image, and then query, like describe image in detail with the grounding image task. So here, when the model will basically talk about the 4 basketball field, it will also basically localize those basketball field. And when user will ask other follow-up question like also localize the trees, it will localize the trees. And then for other follow-up question like is there any intersection, it says yes, there is one intersection, and user will ask where is that intersection, and it say at the center of the image. Here is the image of the flooded area. So question was how many buildings are flooded. Model says 3. So you say like if there are any vehicles or if there are any bridge in the image. So yeah, so model says yes, there is a bridge and there is a vehicle as well. So here is the question is like detect the Boeing 747 plane. So model has to really detect the Boeing plane, special type of the plane as well, and also the buildings if there are the building nearby the planes as well. So here the goal is to basically get the attributes of the any vehicle, for example, their color and the location. And now the demo will show like how we can basically use this region captioning task, where the user will draw a box within the image and ask question about that box. Like for example, user draw a box and ask what is this, like it tells there is a this is a vehicle and so on, and then it will draw another box like what is this. Yeah, and model will say like yeah, it's a one basketball at the top. I have some more qualitative examples from the Abu Dhabi region. So this was image from Abu Dhabi. So the question like on these image model was not trained. These are like yeah, out of kind of distribution example. So question was what is the number of large ships present at the center. So here model has to see like okay, there is a harbor at the center, and now it has to also count the number of ships that are larger than the other ships available. So the model answer like there are 9 cruise ships, and also it tells there are some other small ships as well. This is the image from the Rim Beach. So question was like, please describe the image in detail. So a model starts with like this appears to be a beach, and there are the mangrove cover, and then it talks about like there are some football fields and the football and the basketball field in the middle, and then it talks like there is a highway at the top with the vehicles, and then it's tells like there are a lot of building indicating it's a residential area on the beach line. This is also image of the Abu Dhabi golf course area. So the question was where are the tennis courts and also water body. So we use the refer tag. So it's telling the model we want to basically get the pinpoint location of these objects. So model will basically in the red boxes give the tennis courts, and then in the blue box it shows like there is a water body. We evaluated our model on different zero shot scenarios like for scene classification and weak way task, and we achieved the state of the art performance in these benchmarks. These were also like our results on our benchmark, which was like this was the first work which basically can do these kind of visual grounding, and we were better than baseline manageability. So as we have time, so I will quickly talk like what we can have these potential use cases. Like these are hypothetical use cases which we can extend our GeoChat model to do. So for example, one question would be like power consumption monitoring. So this is the image of area for a Cornish beach. So we are interested in this red box and see like what is the number of the building in that area, and give us like what would be the estimate power consumption. So to answer this, model have to do multiple tasks. For example, it has to first count the number of buildings, and then from its like its knowledge basis it has to guess like how many people can live in this area, like, and then it says okay, then it has to guess like what is the then power consumption in 1 unit or per square meter and so on. And then it has to aggregate all this information and then come up with an estimate value. Here is another image from Masdar City, power plant near Masdar City. So next the question could be like, what is the estimated carbon emission of the given power station and rate in terms of its sustainability? So now the model has to, like also identify the area, like where it is located, and then use its knowledge, like what could be like in this area, how much carbon emission it would be, and in terms of sustainability, how would you rate it? Yeah. And there is another example of like what is the number of ships present. So here model has to see like there is 9 cruise ships present, which indicates like tourist environment with the multiple harbor present in the center. Yeah, so I will quickly talk about like future direction after this GeoChat work. So in the GeoChat, we were only working on the RGB images, but like I started, like I talked in the start, like in the remote sensing, we will have like this time series data set, multispectral data set, and so on. And also we, in the remote sensing, the segmentation task is really important. So the future direction could be in this one of in this direction, and we also this was like recent work we got accepted in the CVPR 2025, so which is all extension of this GeoChat. So in GeoChat we will have only RGB images. Now this orthodile model can have like multitemporal, can accept multitemporal input, can accept like multispectral input, SAR based imagery, and so on. And we also propose GeoBench VLM, which is the first visual language benchmark for these geospatial models. And also we are working on foundation models that will be a global scale, like it covers, it uses the data set from the ESA field lab, naming Major Tom, which cover basically every ground pixel available in on the globe. So yeah, thank you. If you have any questions.
Thank you so much, Mohammed, for your great presentation. We only have time for one question due to the time.
Great presentation on this topic. My question to you is, like you basically mentioned that this software you have created, it's basically you show the image and the AI, the bot will respond to you. Are you using open API sources? Because even if I upload the image, let's say ChatGPT or other softwares, it'll be a bit tough to recognize the thing. So are you using Google source API, live updated API, or?
In terms of like this GeoChat model is open source, code is open source, weights are open source, anyone can use, anyone can extend. So I'm not getting
like the data you're using, is it real data, like live data, like API, like updated, like the Google, like every time it keeps updating, the maps keeps updating? So
okay. So no, it's not like we used publicly already existing data sets which are not like up to date like 2024, but obviously we can use, like we can extend this GeoChat to basically updates like every 6 months or the 7 months and so on. So it can be extended towards those, but right now we only use the available data sets which were like a few years ago.
Thank you.
Yeah.
Thank you so much.
Yes.
I would like to take this opportunity to thank our incredible speakers for today, Dr. Farah, Dr. Dwarikanath, and Mohammed Sohail, for your great presentation and for sharing your research finding with us. Your work is very inspiring. Thank you so much. And this is what ADIA Lab Seminar Series is all about, bringing together the brightest mind to share ideas and push the boundaries of what's possible, to build an interconnected community of researchers and innovators. Thank you again for joining us, and for those attending here in person, we would love for you to stay and join us for iftar to continue the discussion and to catch up further. Thank you so much.